Welcome
Yes.
to Morehouse Metrology Matters. Today I have my son Brett Zumbrum with me. Brett
Hey.
does marketing with Morehouse, and we were supposed to have a webinar today, which did not happen. We had some snafus. There'll be emails and everything else going out. If you're watching this, it's after today. Look, we admit our mistakes; they do happen. So Brett and I are going to deliver this. He's going to ask some questions, and we're going to do like a podcast webinar, put it on YouTube. If you had signed up and we weren't there, it's not going to happen again. We've already addressed the situation, and things are put in place to make sure that we have redundancy. This one is being recorded on Teams. We usually use GoToMeeting, etc. But right now, Teams is working for us. So the topic is PFR, the potential high cost of rework. And this is something for those that don't know a little bit about you, Brett. My name's Henry. If you're watching this, you probably watch the podcast. You know who I am. But just Brett had joined the Morehouse about 2 years ago and had the pleasure of growing up with me and me being grumpy and coming home when we were going through all the culture stuff and the shifting culture and establishing our team and everything else that we're doing now. So, Brett, just a few words about you and
Yeah, so I'm the guy with a little bit of dirt on his face in that corner right there. So yeah, almost 2 years. It'll be 2 years coming up in June of being full time in Morehouse. For this, I go do some summer work, a lot of kind of yeah, just impromptu jobs like fixing some lights around the place or cleaning bathrooms, all that fun stuff. But yeah, getting into marketing with Morehouse over the past few years, and also in my spare time, learning some force calibration as well. I'm still a force calibration tech in training. Whenever I have spare time and the guys are in the lab, they help me out. I'm learning some pretty basic calibrations, and I'd say pretty inexperienced still, but getting there.
Yeah, so this is a little bit different from us because Brett does have some experience in the lab, not much, and there's probably a lot of other people that are in his situation. He did grow up with me. He's edited some of the posts. He does handle the marketing, so he sees this stuff, but probably does not correlate everything that goes on and what it means. And that happens. It took me 10 years until I kind of put it all together. I work in the lab. I know load cell wiring. I know calibration. I know lots of things, but to put all of this together, what's PFR? What's risk? When we start talking about likelihood and consequences, why are we doing this? Why do we do this? And then, getting into lean and some other Six Sigma and some other stuff. But anyway, our purpose, Brett, you want to say what that is?
Yeah, sure. So we create a safer world by helping companies improve their force and torque measurements. So I've seen it firsthand, editing some of these blog posts, some of these podcasts that have been made before, and also hearing Henry himself talk about some catastrophic failures that resulted from poor measurements.
Yeah, so everybody comes to work with with a purpose, and this is part of it. Like what we want to talk about is like PFA, PFR. What is this? I mean, you're watching, you're like, what is PFR? But I want to this hybrid approach of giving you a little bit of metrology matters, which will go a little longer, and the webinar type of thing, and knowing that Brett has looked at this, but he knows, I would say, very little on PFA, PFR, and what it means, and what it means for you. So, simplistic terms, PFA is the chance that when you actually pass something, that it's wrong, meaning that it could actually fail. A lot of companies pay really close attention to this. We live right down the road from a cookie company, and guess what? If they underfill their product, they get a fine. So what do? They overfill. Well, overfilling avoids the fine, though they're sending out extra. So when it says 16 ounce, 19 ounce, whatever it says on it, they're making sure they put a little extra in so they never pay that fine. Well, that extra adds up over time. PFR is the chance that when you fail something, uh, that it is wrong, meaning it could actually pass. This is that thing that such a thing your cal provider says from one calibration to the next, uh, the instrument failed, we adjusted it, and now it's on you. You have to deal with the recall. This is what really sucks, Brett, for a lot of other labs and stuff. They send it to a lab with maybe lower measurement uncertainty. Somebody thinks they know what they're getting, or a lab, a new time technician, like they just give it to Brett and say, hey, go do it. And without that much training, he puts it in a machine, says it's bad, doesn't read all the notes or doesn't know all the steps, procedures that were trained on it, send it out to you, the end customer, and then you get this fail. You said, oh, by the way, we adjusted it. But if it wasn't really bad and we adjusted it, how do you know it's good now? So that's the risk of using laboratories with high uncertainties, with untrained technicians, doing all of the stuff that may not make sense. Does that make sense, Brett, to you as you're
Yeah,
back and
yeah.
forth?
So through just my, of course, mild level of experience, I know that not every force instrument is created equally for what calibration procedure you need to follow. So a single run calibration isn't the same as an ISO calibration. There's different steps, there's different procedures, there's different ways that you interpret the data. I mean, it's not a one size fits all. So for somebody like me, I'm a little bit more advanced past that stage where I know some of the differences and I can read specific, uh, let's just say sales orders, right, to differentiate what steps I need to do, and I know where to ask for help, of course. So yeah, not every calibration is the same. And if somebody's just looking at them like, hey, I'm just gonna push a button, or hey, I'm just gonna do this load cell how I do other load cells, you could be getting the wrong calibration.
Yeah, you could have wired wrong a lot of stuff. So that's PFA, PFR. Now, this gets confusing because there's this term global. That means out of a population, producer risk, which means out of all the truly intolerant items, a percent that's rejected. And then specific false reject probability is given the result plus uncertainty chance it's actually intolerance. And we'll go over these in more detail, but most guidance focuses on PFA, false accept consumer risk. Again, that's the one that's saying, hey, we're putting a bad product. If we want to limit this, PFA is I'm saying something's good when it's actually bad. And companies will go to great lengths to make sure that doesn't happen. That's usually like the large uncertainty guard bands that are probably, this is biased opinion here, that may be too aggressive. And then your PFR, guess what? You put a aggressive guard band on something, and now you're going to reject more items that are actually good. So, and say they're bad and adjust them. So this webinar is going to highlight our conversation here with the screen's going to highlight the false reject producer risk, hidden cost, rework. We'll connect the measurement uncertainty, decision rules, and guard bands. And the strong point here is anybody in life, in anything you do, you run a business, you work for a business, you're part of the team or whatever, is that risk is always a business decision, or is always a decision involving likelihood and consequences. So Brett steps outside. It's kind of cold out. It's warmer weather. There's still ice melting, but Brett steps out outside today, and if there's ice on the ground, what is that likelihood and consequence? What is the likelihood he's going to fall, and what's the consequence if he didn't salt? Things like that come up um, all the time. But in your business, there's a lot of that happening. Are my exit signs illuminated? If the lights go out, can people find the way? A lot of things. We just replaced all our exit signs, so we have
Oh,
that. So, um, measurement confidence. So this is from the principle, it's good to great. What are you passionate about? What can you be the best in the world at? And what drives your economic engine is the principle in good to great. But we took this for measurement confidence and, hey, I have to know my uncertainty. I have to know the traceability, where did I propagate that uncertainty correctly? Did I have a measurement performed by an NMI such as NIST? If did I have it by somebody else? Who did that? Who did theirs? Did they propagate it? And then what is my decision risk? What is that likelihood and consequence? Am I giving that right for everybody? So there's three pillars. Those are the three. And if we review them quickly, these are available online. Measurement uncertainty. This slide says the range within which the true value probably lies. Um, you know, if we want to claim it, we trace it back to SI units, not NIST. Some people say traceable to NIST. We all know that's wrong. I'm sick of saying it, but there's language in contracts that say it. So nothing is traceable to NIST directly. It's traceable to the SI units through an NMI, and they're documented. So uh,
Right.
as this goes, you can see the uncertainty gets larger. Measurement uncertainty, typically the CMC uncertainty parameters are defined in several documents. ILAC P14 is one of those. The general GUM, Guide to Uncertainty of Measurement, it's repeatability, resolution, reproducibility, reference standard uncertainty, reference standard stability, environmental factors, and other. So Brett, you know why I put other here?
I can't say.
Because this is your catch-all to get so no one can yell at you and say these are wrong and everything else you mixed out transport uncertainties, you missed out this, you missed anything else. You can basically say it's under other, but we have our 5 R's in our E, and then there, of course, depending on the instrumentation and what you do, there could be other things that impact. If we look at ISO 17025, when Brett said ISO earlier, he meant ISO 376, which is
Yep,
a
yep,
force
yep.
standard. But
I didn't want to
la-
mess up the numbers right off the top of my head, so I said ISO, didn't want to have to get
so
corrected.
yeah, a lot of people assume 17025, which
Hmm.
761 laboratories shall identify the contributions to measurement uncertainty when evaluating measurement uncertainties. All contributions of significance, including those arising from sampling, shall be taken into account using appropriate method of analysis. So, Brett, what do you think significant is?
Well, that's kind of hard to say. I mean, significant for one person might not be significant for another person, and something that's not significant for one lab might be significant for another. It all depends on your application and I guess what your field is.
If I told you we were going to cut your pay by 5% per week, would you say that's significant?
Yeah, I consider that significant.
So, what about if I said 1%?
It's still significant. I'd say that cutting pay until it gets down to probably the hundredth place is still going to be significant. You're still going to somewhat notice it if you're going to look at your checks every week.
Fair enough. So, some of guidance documents, they come up with like, what is significant? Well, if it's 5% of your total budget, or if it's just 5% overall. But even if Brett said 1%, but let's say it was a half percent. If I cut Brett's pay 0.5% and I continued to do it, eventually it becomes very, very painful. And if you have a lot of contributors that are like 0.5% or 1%, 10 to 20 of these contributors, that could be a good sized portion, especially if 5%. If it's insignificant at 5% and I have 10 items that contribute to 45% of my overall budget and I just discard them, that's pretty significant. Anyway, I'll get off of that topic there. But um, so load cell with measurement uncertainty. We're going to eventually use this load cell, and we're going to calibrate it with primary standards, which look like this. Dead weight machines, which how many of them are in the lab there, Brett? For
So
questions
let's
for
see, you have your 120 LBF. Then I think we added the newest
6,600,
one, the 6600. So, and then there's the 100
12,000.
pound,
Yep.
1100.
Yep.
So the
Six.
30K. Yeah, so what's that? One,
Our
two,
lab has 6
three,
dead weight
four,
machines,
five. Yep, six in total. You're right. Yep.
up to 120,000 pounds. Now, these dead weight machines are primary standards, which is defined by ASTM as weights that have been calibrated using with considerations for the material density, adjusted for local gravity, air buoyancy, and that are machined with a surface finish according to ASME. That's basically generalized finished. Any turning center usually achieves. Uh, so if we look at this and look at our 5 Rs, they're there. Morehouse CMC would be the reference uncertainty of our dead weight machine. That's really low. Overall contribution to everything for this load cell. Um, our reference standard when we put it in our dead weight machines is 14.43% of the overall contribution. This is using the Wells-Southard equation, which is found in JCGM. Just look at that, say, okay, I got my repeatability, my this, all the other stuff, the 10,000 pound load cell. Now, do the same thing. I could use BCM. It's our benchtop calibrating machine. It's a manual machine. It cannot be automated. It's fairly quick, easy to use. It'll perform calibrations. Um, Nowhere near as good. That other machine was at 0.0016%. This one, I'm going to show you this. It's going to say oh 04. Most people achieve oh 05. We could say we're better than most people, but the fact is we just have a ton of experience in using the machine. So if you purchase this machine, you're typically going to be around the oh 04 to oh 06. When your technicians get really good at honing in on the forces, you probably get things down to about oh 04. But assuming other things stay the same in this whole scenario, and all we've done is changed our overall CMC uncertainty parameter from 0016 to oh 04, Brett, what do you see as part of the contribution here? If
I
I
see
did,
that
yeah.
at least what I'm seeing right now. If at least we're on the same page, I see that large highlighted blurb. That's 95.74%.
Yeah, so it was 14 and change percentage, and then we changed, all we did was change our reference standard, and now 95.74% of our, or the overall uncertainty of calibrating this load cell, assuming nothing else changed on the load cell, it's still as repeatable and everything else, and they can do this, is 95.74. In actuality, what's going to happen is over here, the repeatability is going to get a little bit worse because you just can't control the force like you can with a primary standard. You're just sitting the weights on something, and they do oscillate, but it's very low amounts of drift if the indicators are stable and have good filtering. When you have that
Right.
other machine, it's harder to control, so the repeatability goes up a bit. But if we're looking at this, we do the calibration with our deadweight primary standards. These overall contributors, nice graph over here. We do that versus somebody else doing it. Overall contribution looks pretty close, right, Brett?
Yeah.
So this is where graphs and learning to understand graphs come in. If we
Oh
look
yeah,
at
at the
the
bottom
scale,
portion. Oh man.
it's not close at all.
Wow.
Um, yeah.
When you're
And
glancing at it does, but yeah,
when
once
you
you
go,
look into
yeah.
little details, it's what I said earlier. Not every calibration's created the same. It's if you don't look at the little details, you're gonna miss a lot.
So if we just look at that right side, accredited cal supplier, everything else, you say, oh yeah, that's the majority. But until you know the scale, it's a little bit different. So if you ignore the numbers, but the whole piece of this expanded uncertainty when calibrated with primary standards, 0.41 pounds force, and then calibrated with that benchtop machine, that same load cell, when we do the traceability aspect and do uncertainty for it, is 4.03. So this is almost a 10x multiple overall. But it is important to look at those graphs and everything because the side on the left, this is really good analysis. I'm not going to get too far into it, but if I wanted to improve the uncertainty when I'm on the left-hand side, what do I focus on? What's the largest thing? The stability. That's the frequency of calibration. If I have a 2-year interval and I'm not happy with that 0.41 pound uncertainty, maybe I need to shorten it. Most people would love a 0.41 on 10,000. So whatever the interval is on this, you'd probably be happy with it. But if you did want to do anything or improve the system, that graph tells you immediately that that stability is the thing to tackle. On the right-hand side, what's it say? The largest thing here is basically telling me I need to change my calibration. If I want a lower uncertainty, I need to change my reference standard I'm using or my calibration supplier. So Brett was one that ended up doing this, the load cells. When you see angry load cell, happy load cells in love, Brett has designed those cartoons.
Yeah. No AI for that one, just done through digital software, pretty much make the different shapes and then make the avatars.
Yeah. So this one is the PFA, which is saying something is good or conforming when it's non-conforming or bad. An example, a cracked bridge cable gets marked as safe because the test wasn't accurate. The mistake can cause dangerous failures, recalls, and harm trust. Brett drew that machine with some duct tape on. We've seen it. We do have.
Exaggerated, of course. Yeah.
Is it exaggerated? You've edited one of our latest blogs that has
Yeah.
like the what not to do, and it has someone pulling something in tension with a forklift that was a compression gauge. So look for that one if you want to
Well,
see
to
the.
keep peace of mind, you'd like to at least convince yourself that this machine is completely exaggerated.
Yeah, they happen. People use it. They weld things they shouldn't weld. So down here, we're going to talk about this later. A low TUR/CM. TUR is test uncertainty ratio, and CM is measurement process capability. The reason CM is listed there is because JCGM 106 says, hey, TUR is such a butchered term that we should start talking about CM, which is measurement process capability. Probability of false reject, saying something is bad or non-conforming when it is conforming or good. Also known as false reject risk, probability of an intolerance item or parameter being unknowingly rejected by testing or calibration. This is the title of this slide of this presentation and what we're talking about. Perfectly fine medicine bottles get thrown away because the measurements said they were off. The mistake wastes time and money on rework that is needed. So unnecessary rework, what do? You waste time and money. You're running a cal lab, you're telling people their stuff is bad and you're adjusting it. You may have an adjustment fee, and management people above you may say, we get paid to adjust this stuff. We can charge people for it. It's a good thing if we reject it, right? Well, what customer wants to use you if you're rejecting their stuff all the time? What headache are you passing to them? And like if I'm throwing out equipment, when I was in the Six Sigma classes, I'd run into this all of the time. Where people would just overrun stuff. They wouldn't care. Oh, we'll sell it eventually. And the people that were in the class, when they were able to show the return and sometimes $500,000 or more dollars, it was significant. Greg Senker and I do a decision rules class. Brett, I don't know if I ever told you, he found $1 million a month mistake for one of the bigger companies that they were saying stuff was bad when it was actually good. So lots of fun stuff there. But yeah, simplified. The chance you say something fails when it's actually conforming. Why the labs feel it, tighter tolerance plus moderate test uncertainty ratio, inflate uncertainty relative to the higher tolerance, narrow acceptance zones. Um, these are things that happen. But the highlight is reference CMC quality. Primary versus secondary standards can swing your expanded uncertainty. So they're going to set your guard bands. And I'm just going to move right on to that when we talk about it. Specific risk. This is one curve. So, Brett, whenever we look at things on a level of like global or specific risk for most people, if you think about who do you like, football or basketball? Who's someone you really like?
I mean, there's a lot of star players anywhere you look. I'm more of an NFL guy myself,
So who?
Steelers fan. So, we'll just go with Aaron Rodgers because
So let's go
he's
with okay. So let's
current
go with
quarterback.
Aaron Rodgers. Aaron Rodgers takes one throw and it's 40 yards downfield in this center. He's throwing at I don't know how big the targets are in the NFL. Let's just say he's trying to throw a football through a 3-foot target 40 yards down the field. Okay. So specific risk is really easy. He threw the ball. Did it go in the target or not? Right? One throw. Is it in or not? You get it? You good?
Yep.
Okay. So he throws the ball. It doesn't go in the target. That's a fail. He throws the ball. It goes in the target. It's a pass, right? He made the target. So he throws 3 balls. They all go in the target. What is the percentage out of those 3 throws? What is the percentage that he got in the target? All 3 went in.
It'd be 100%.
100%. Okay. So each of one of those throws is a separate response. So a specific risk is based on the specific measurement result. Aaron throws the ball, it either goes in the target or it doesn't. Um, it's gathered at the time of test. Characterized by 1 or 2 probability distributions depending on the method. Any represented with 1 probability distribution is always specific risk. So Aaron throws the ball, it goes in or doesn't go in. So now we deal with global risk, also called process level risk. Based on future measurement results, it is used to ensure acceptability of documented measurement process and based on expected historical information and usually characterized by 2 probability distributions. So this is where Aaron throws the ball 100 times a day and 95 go in. What's that percentage, Brett?
100 times, so that would be just 95%.
95%. So 95% of the time it goes in. He does this for weeks on end. That's pretty freaking impressive, right? Throws the ball down the field, it goes in, goes in, goes in 95% of the time. So that means 5% of the time it does not go in. So global risk basically says, hey, I'm using all of this population data and I have distributions that basically tell me there's a 95% chance that when Aaron throws that ball, it's going in. If by chance it's tomorrow is Wednesday, he throws that ball down the field. First time out of the gate, he throws that ball and it doesn't go in. Using both of these risk curves, someone's going to tell you it's actually in. And that's where it gets confusing with these measurements because you have all of this historical data that's based on probability and the knowledge that's down here that's telling you, even though I'm saying my measurement this one time, Brett put it in the machine and it's showing out based on all of this historical information that I have weeks and years and all this of data of this similar instrument. It's these curves it's actually in. And it's hard to struggle with. It's a little bit more difficult to struggle with these theories. But that's what it is. If it's a critical situation, like he's hitting a receiver down the field in the end zone uh, to win the Super Bowl, we can only dream, right, Brett? So,
Yeah.
and the guy's open and he misses the center of the field that 5% of the time. They're not winning the Super Bowl. The officials aren't going to go, hey, timeout. You know, since the probability of this is 95%, we're actually going to give the touchdown when it didn't go. That's not happening. So if you were making defibrillators that go inside your body, you probably wouldn't be okay with using global and saying, yeah, there's a 95% chance that what we just put in your body is okay. Like I would say pacemaker. right? You're going to be like, I don't want the 5% that's bad. How have you tested this? Oh, we're using population data. Anyway, so specific false accept risk given the measurement result and uncertainty, what's the chance the item is actually bad? Global PFR of all the truly good items, what percent do we reject? Right? That's really, and if you start getting higher uncertainties and everything else, we're going to go into that. So specific false reject risk, given the measurement result and uncertainty, what's the chance it's actually good? Keep saying this stuff. So one of the documents, Brett, ILAC G8, it's to 2019. I think they are rewriting. There's some definitions, a tolerance limit. So that specified the upper and lower bound of permissible to property. You've dealt with this, right? All the time. Someone sends something in and says, I want plus or minus 5 pounds, or they give you, what are some of the other examples? A percent of reading, the
Yeah,
MSI
percent
stuff.
full scale is one of them that you'll see. Um, I'm blanking on what the other one is off the top of my head.
IV indicated value of
Mhm.
reading. There's some people bracket depending on the capacity, but typically manufacturer's going to say, hey, this is good to 0.1% of full scale. So you say, great. And someone's going to send you a PO that says calibrate to manufacturer spec. And you say, okay, fine. Well, that's the tolerance. The acceptance limit is the specified upper and lower bound of permissible measured quantities, lower specification limit, and upper specification limit. Measured quantity value is what I actually measured. The guard band is the interval between the tolerance and the corresponding acceptance limit. So the decision rule is how the measurement and certainty is going to be accounted for. And if we draw this out, lots of stuff there to think about. There's my tolerance limit, right? This is manufacturer spec. This is, or somebody else might have raised the manufacturer spec. They said they're telling you something for the measured point. The acceptance limit is basically, hey, there's a level of risk I can live with. Calculate this out so my PFA is less than 2%. They could say 5. Typically, most standards are written that say 2. And then I have a measured value there. So if we're using the Aaron Rodgers scenario, it's basically saying that my tolerance is probably, depending on how good my receiver is and everything else, maybe the best receivers in the world can be within a 5-yard range of this throw, but I gotta hit my throw in the end zone within maybe plus or minus if the 5 yards total, that would be plus or minus 2.5 from center. And we'll say on this one that now my receiver's not that fast. They're it's DK Metcalf, and even though he's awesome, he's not as fast as say a Calvin Austin or somebody else. So now I got to hit that. I can't be plus or minus 2.5 from center. I have to hit it plus or minus 2 yards from center. And as long as this measured value right here is between that, I'm good. The risk of that receiver dropping the ball is because they're so open is going to be low. You could think of it that way. I'm doing this off the top of my head, but my measured value, I'm subtracting something. I'm subtracting enough uncertainty from the tolerance limit to control my risk. There are downsides to all of this, but this is typically what's called the guard band. I want to make sure I limit my risk to X. You have any? So if we can look at this another way, is basically says as my uncertainty increases, my conformance zone decreases right down here. I don't know why it drew what it drew there, but does this make sense to you, Brett? And I'm saying this for most people because Brett is not seen all of this before, and I think this is a good opportunity to
Yeah, right.
explain this.
Or I've glanced at it. I've gotten somewhat of an overview, but I haven't gotten into actual specifics. But yeah, it makes sense to me that the bigger that your uncertainty gets, of course, the smaller your conformance is going to get. You know,
Yeah,
you're probably not going to be within tolerance, or I shouldn't say probably not. You're more likely to be out of tolerance if you have a bigger uncertainty.
right. And if I have the best equipment, like maybe, I don't know who's, I'm going to be insulting here. Puka Nakua is a really great receiver. He might be the best receiver versus somebody else.
I don't know,
Maybe,
JSN,
yeah, okay, from Seattle. So
Seattle, yeah.
maybe I can have a little worse of a throw up here and still have my receiver catch the ball. So I can have, with my uncertainty being low, I have more room to say something's intolerance and better chance of it passing, which for you or your customer base means there's less chance of me dealing with a headache that somebody said, hey, this was bad when it's actually good, or this was good when it's actually bad. So all of this stuff, uncertainty is like one of the biggest driving impacts for overall risk when we talk about likelihood and consequences. Uh, Essence of decision risk and conformity lies in ensuring the final product's quality, accuracy, and durability. It's a quality where both the likelihood and consequences of failure are evaluated, often using a risk matrix. In many cases, the measurement that is made can be thought of as the likelihood. The consequences that happen after can be severe. So, um, let's talk about things in our, let's talk about some more fun ones, as far as business decisions. So, if my exit sign is not lit during the day, and I have a power outage where people need to evacuate the building, but I have windows in the building that are letting in natural daylight. Would you say that the emergency lights going off, not going on, would be negligible?
For the most part, you're going to have your exceptions too, depending on if somebody has impaired vision, because you got to analyze that too. It might be harder for them to see those, but I'd say typically, yeah, it would be more negligible.
Okay. So, what about if we had a diabetic in our, um, as part of our team, and they started having um, a spike, the low blood sugar, where they collapsed, and we didn't have a sugary drink to give them.
That's certainly not negligible. I mean,
No,
then you'd
it's
have
pretty
to,
severe.
yeah, you'd have to find who can go out, who can run out what's close to us. I mean, we got a cookie place right down the street,
We
luckily,
do.
but still that's taking minutes, and minutes matter, seconds matter in that
Yep.
situation, I'd imagine.
Well, we had our CPR training, so let's do the AED devices that we have. Like we have two buildings right beside each other. We have an AED in each building, right? Not having the AED, if somebody went into cardiac arrest, could be catastrophic.
Right.
So, if I'm using a force gauge to verify a 1% machine and my device is a 0.5%, and I made the wrong decision on this, and I really only needed my measurement to be 5%. You think that's a severe consequence if something's good? If I say it's good when it's actually, instead of 0.5%, it's actually 0.6, 0.7%, when I need a measurement to be 5%?
So let me just clarify here because to make sure we're on the same page. So
Okay.
you need it within 5% is what you're saying.
Okay. So my device's
Or
spec is 0.5%.
okay.
I'm saying I have high uncertainty, and the best I can do is 0.7%. And the end result, the end measurement, what I really care about is a measurement that's 5%.
Is I want to so I'm going to say that if it's less than that 5%, that you're still okay, or am I incorrect to say that?
Maybe. I think these numbers are so far apart that
Yeah.
my risk is really minimal. If we take it's not good practice by any means to say to do if it's a 0.5% and the best you can get it with all the stuff like we showed in the graph is 0.7%. But if you compare that to somebody that wants like a dynamometer or something. So let's compare that to somebody that wants 0.1%, and the best measurement scenario the company that actually is performing the measurement can do is 0.7%, and the end customer wants the device to be, man, that's just drawing things, half percent, right? This is
Yeah, that's a pretty big failure.
that's a big failure, depending what it is. Like if it's just for scale that's like just or something. It's
Yeah, but
all
in terms of
dependent on
meeting
what it.
customers' expectations, that's still a pretty big
That's
failure.
high. Yeah, that's a high level risk. But for the customer, what if that event is just a scale that weighs says if something can go on a truck or not? What do you think happens there?
Yeah, I mean that all depends. It still increases your risk most certainly for that truck. I mean, if
Maybe.
if what yeah, you're right with maybe because if that's the only thing that's going on the truck and it's rated for 100 times that amount, even if it's with out
Right.
of that spec, then you're fine. But if that truck's loaded up to the brim and you load in that last thing and that's above its capacity, even though there's probably somewhat of
Yep.
safeguards, but if it's old, if it's been in commission for a long time, who knows? You might pop a tire on your way
You
there.
might pop a tire. You might, if you hit an icy patch, you might not be able to stop. You might slide off the road. You might create damage to the highway. You're almost certainly, if you stop at a weigh station, which are all along major highways, you're likely going to get a fine for being overweight. So getting a fine for being overweight, your consequence might not be. I mean, the likelihood of that is almost certain, right?
Hmm.
But the consequence might be a
It's
minor.
more minor, yeah.
But you blow a tire and the trailer tips over and somebody kills somebody, that's catastrophic. So this is hopefully as we talk through this is risk, and not it doesn't always happen the same way. There's times where people get away with this for the longest time, and then when they stress the system or stress the truck by loading it to capacity, that these improper measurements really show their ugly head, and it makes a big difference. We had done some work with flying, if people remember, some people unfortunately died because cables snapped. And then we had, after the fact, we had done some work with the company to make sure, and their tension links to make sure everything was good as long as that show ran. There was a wrestling event where a wrestler fell from because they weren't strapped in. The cable broke. So that's pretty severe consequences. Decision rules are not required. I mean, they are required, but there's things. If you want to make a conformity assessment, a decision rule is required. So for statements of conformity, labs must document the decision rule employed, taking into account false accept and false reject. If the rule isn't standard, it must be agreed by with the customer. Guard banding is optional. It's one way to implement the decision rule. Just know this, tighter guard band means that lower consumer risk, less chance of saying something's good when it's actually bad, but you have the higher producer's risk where we're going to say more instruments are bad when they're actually good because we're guarding really, really high amounts. And I'm going to show you graphs with this. So expanded uncertainty in our dead weight machine, going back to this load cell example we did eons ago, we had these two uncertainties, 4.03 and 0.41. The dead weight machine, lower uncertainty. Aaron Rodgers throwing, he's got like, there's so much with JSN, I think you said, there's
Yeah.
so much room, right? He can be off by how many yards? In this case scenario, we're talking numbers. TUR is like 20.83 to 1. I'm going to switch to the highlighter. But whereas, like, now you have, you're making knocking him, but now you have your DK Metcalf or something. He needs to be right on target, for lack of better. He's better than that. But
Yeah,
in this
we'll
scenario,
use
yeah,
somebody else. Come on, that's a little bit degrading towards DK. I
it's
mean,
not.
uh, let's just use somebody who we won't put anybody under
Scouting.
throw anybody
Yeah,
on the
no.
bus. We'll say somebody who was just maybe the
We'll
wide
say I'm
receiver
on the
one's
field.
injured. Yeah,
And
he's
we'll
he's
say
on the
I'm on
field.
the
Yeah.
field, and the only way I'm catching that is if you put it so directly close to me that I don't have to run to either side to catch this ball. But
Yeah.
in this situation, there's risk just by doing nothing on this instrument, which the specification here was plus or minus 5 pounds out of 10,000, so 0.05%. In this case, no matter what I do, if my measurement is dead centered over here, I have risk and it's over 2%. In the case to the left, I don't, I mean, I have forever to still say this is good. In the case to the right, there's a strong chance that I'm going to say something's good when it's actually bad or bad when it's actually good. If I move that location of the measurement, which I did here, the measured value to 10,004, last time it was 10,000, the story gets a lot different. We, as Morehouse with dead weight machines, woohoo, we're so great, can still, and because we have these high TURs on this device, we can still say that instrument's in. Another supplier that's using that BCM, it's a good machine. I don't want to knock the BCM. It serves its purpose, but
Right.
if you're using trying to say something's good to a 0.05% and the best you can do is 0.04%, you do not have much room on either side, as we're showing you, to say that device is good if you're applying any type of guard band whatsoever. And if you don't take uncertainty into account and you give this to somebody and say, I measured it and it read 10,004, this curve is saying specific risk curve is saying there's a 34.47% chance that you're saying it's good when it's actually bad. Is that a number that you want to take back and look at that likelihood and consequence matrix? And is it critical? That's what you have to decide. I mean, if it's a truck that you're never filling to capacity, maybe it's not as critical. But if you're filling something to capacity or making something, maybe this is a absolute deal breaker. You're launching something into space. You want your satellite not to wobble. There's so many examples here and here on this, but when the lab with that 0.05% CMC, the risk goes 4.66 to 34.47 with just that shift. Is that clear, Brett?
Yeah, that makes sense to me.
Okay. So if we want to look at this overall, these are fun risk tables. So this is that primary versus that a secondary. So Colin and people, excellent people at Sandia, we'll send us the link in YouTube. We can put the link to this. There's a program called SunCal, which you can put in all the risk stuff, and it does global and specific risk. Our risk curves are in here. This is actual product run through it. The scenario TUR 1 to 21 to 1 and 1 to nothing. But what this does that specific risk curve didn't, you put in some other things, measured value, specific risk 0, worst case risk is 50%. What do you think that means? That worst case, it's for both of them, is 50%. Any idea?
Um, to be honest, uh, what is that? Just a 50% chance that it fails?
That's a worst case if I'm using specific risk. What that is telling me, that says if I run this up to the tolerance limit, half of my is going to be out at the tolerance limit. And it doesn't matter if my TUR is 21 to 1 or 1 to 0. At that tolerance limit, I have a 50% chance of it being good when it's actually bad or bad when it's actually good. This is something that we typically do not want to run up to the tolerance limits. Right
That's
before the
gambling.
yeah, and right before the tolerance limit, the one to the left is saying, my goodness, very, very low risk overall. And in fact, if we run these risk curves, the global risk, how many zeros is that? One, two, three, four, five zeros in a one. Super low number. Where if I look at global risk, remember taking shots every day and I'm missing some, this is saying on a global risk over here, the PFA is 1.8%, but the PFR is 13%. So I'm applying some type of guard band, and the specific false accept risk 34%. That's what we had the last time. Process risk, other things. So basically, that's saying that okay, I can kind of control my risk here, and though I'm going to call the penalty here because I have such large uncertainty is back to the PFR. It's saying on a global scale, I'm getting 13% of the population. I'm going to make that wrong decision. I'm going to say is actually bad, and they're going to be good. So if we look at the impact, the easiest way to sum it up is I have that large acceptance interval. Um, and if I have something that has severe consequences and I evaluate my likelihood, if it has severe consequences, it's on risk decision. Even likelihood, I'd probably search out the best standards to calibrate that device. If I'm maybe don't need to have that level of risk, uh, maybe I go with someone that has larger uncertainties. And if I have like cheaper to buy, costlier and false decisions, that types of stuff, maybe I'm okay with. If I don't have that severe consequence or the high likelihood with that consequence, maybe I'm okay if I'm just, using, if the end result is a 5% measurement and the lab's giving me 0.7, even though the tolerance is 0.5%. I probably am okay with the lesser. Hopefully that makes some some assessment of sense. So looking at this another way, guard bands are dial, not a switch. You can use them to meet PFA targets without starving throughput. Um, more things on measurement decision risk. This is my dream scenario. I know Brett has looked at some sales orders and everything else. And when I say my dream scenario, is somebody understands the likelihood and consequence so they know their actual risk, what they want you to do with their device, and they write something like, hey, please calibrate as found, manufacturer 10,000 Newton load cell, serial number with this readout, in compression only, and issue a pass when using specific risk greater, less than or equal to 2.5%, otherwise fail it. I would say that we've never seen a certificate or never seen a purchase order that has been this
No.
descriptive, and I would love to see one. This basically is telling us, hey, I have a 10,000 pound, 10,000 Newton cell. My measured value is 10,008. Area outside the curve is 2.275. Guess what? Their decision criteria is what here? It's in. It's less than or equal to 2.5%. We issue a pass. The customer agrees on the pass. The risk is below that. We're great. We see more of this type of things in our scenario where you have this 50% scenario, and this is the tolerance limit. Doesn't matter. This is a resistor example from JCGM 106, but in this case, the tolerance is the same as the measured value. And all the time, when we look at this, guess what? 50% is outside the curve. Now, on our bench level reality with no guard band, the odds of a wrong decision approach 50-50. Half the time you falsely accept it, half the time you falsely reject it. If we brought in This is just specific. If we brought in that population data, Brett, what happens? We bring in that population data that's drawing curves horribly.
Yeah.
That's over here. Guess what? That risk, that global risk shifts us. So it's no longer 50% because we're looking at the whole, all of the throws that Aaron has made over the years and everything else, not just the ones he's making today. So um, can hide things.
Yeah.
And then the types of errors. This is a good, generally when you have this called accept, reject, a lot of the same thing. Conforming, non-conforming. Look, these are the good. The green are the good one. Hey, when something's actually bad and it needs fixed, we fix it, calibrate it, get it out the door, and then when you send it in and we say it's good, there's no doubt, right? Well, there's always some doubt, but there's very little doubt. More than likely, you're good to go. It's this when you get to this side of things, when you say something is good when it's actually bad, or when you say something is bad when it's actually good. Guess what happens? You do uh, unnecessary rework, and Brett did this little cartoon where money's just lit on fire because that's really what you do. If you pay somebody to work on good products that you said were bad when they're actually good, it's just a waste of their time, everybody else's time, and a waste of all of your dollars. So they're generally two types: consumer risk, so many names in this industry. Uh, Type 2 error, you learn that in school. Most of us have pass error, false accept risk. PFA, we had to make PFA another term, can have potential negative impacts. And then producer risk, type 1 error, fail error, false reject risk, probability of false reject, has the direct impact on manufacturing and everything else. If we want to fine tune our PFA, we can do things like measurement reliability. We can look at our calibration intervals. We can buy better standards, lower our process measurement uncertainty, calibration adjustments. If it's too close, maybe we have some run rules. We can implement guard bands. This is all from, if you don't have this paper, go out and get guard band methods and overview. It's quite an excellent paper. Consequences of PFR, stated this several times, is you're calling something bad when it's good. Your calibration provider gave it to you. They did the unnecessary rework. They adjusted it. And now you're being told it was bad. They adjusted it. You're told it's now good. You use it to make measurements, and it's probably really bad, which is the proverbial word salad mess on all of this stuff. So what you need to know is you need to deal with that out of tolerance report. Might mean that, hey, I got to recall product or calibrations that were actually good. And the big thing is, what if you're risking with something? Hey, guess what? Someone in accounting said, I only want to spend $10,000 on a reference standard. When I actually, if I would have spent 20,000 on the reference standard, I would have a much larger window and I would not have to recall anything. So just things to think about, hopefully that you are. This is from the ANSI 54.3 handbook. I put this in here. Sometimes I like to glance over them. It basically just shows you what we're talking about when we're talking about TUR. It's the reference standard uncertainty, the resolution of the unit under test, the repeatability of the unit under test. And here you go, Brett. Here's the other, so people can't throw us under the bus. There's other things in there. If you look at this definition, the calibration process error includes temporary and non-correctable influences occurring during calibration, repeatability, error in measurement source, operator error, error in correction factors, environmental influences. Hence, it's a lot easier to write other than try to do this equation and gather everything and anything that could possibly be an error. So, simple definition of TUR. When we start looking at what TUR does, for it's qualified. It's the your exact risk is going to depend on decision role. and that the only thing I think we can all confidently say is that a lower measurement uncertainty will reduce your overall measurement risk. Um, ITP, which is ITP, EOPR, which is intolerance probability, EOPR is end of period reliability. That's historical information. That's basically saying, hey, I made 95% of the time this passes Cal, or 95% of the time Aaron Rodgers hits that throw 40 yards downfield into the bucket. And we can use that information to do both of our curves. But if we look at this, you can see as the TUR, easiest thing to tell you, as the TUR increases that ratio and formula, our risk goes down. And Brett, what are you seeing here? If I had a TUR of 1, right,
Yeah, your risk is
risk
going
is
to be
high.
higher.
And the
Yeah.
PFA and PFR are really, really close, right? And this depends on like how I guard band and some other things, but this just,
What's the
yeah.
highest you can get your TUR up to? Is there like any kind of uh
Oh,
maximum that the industry
that's a good
has,
question.
or
There were some mill standards at like the 10-to-1, 4-to-1. The example I just gave was an actual real life example where we were 20-to-1 a lot, and that was an '05 measurement. There's a lot of times where we're in our lab and you'll see, and you've seen some of the certificates that were 40, 50-to-1.
Mhm.
I don't know what it caps out at. I've not seen, I mean, the larger that tolerance gets, because it is the ratio, if we go back, it's a really good question. So if we go back to this, so the larger this tolerance gets, you're dividing it by this, that numerator by this denominator. So
Right.
if somebody sent us something in for Cal that they said, I need 10% of full scale, the number would be, and we're at 0.0016%, divided out, I mean, we're talking what, thousands? So yeah, just
Yeah.
depends on those two. The
Right.
uncertainty you're only going to drive down so low. Like NIST can drive their uncertainty down to 0.001. Um, so that's lower. If we're at 0.002, they're at 0.001, and they're twice as good as us. So if we say our TUR is 20-to-1, this would be 40-to-1 on that same instrument. So yeah, but good question. Yeah, you can keep driving it down. Here's
Right.
an example. This is an example Greg Sanger and I did. The CM, which is the same thing as TUR for all intensive purposes, is you bought an indicator. A salesperson comes in and says, let's go. They go the Acme standard indicator. They go in and they say, hey, you're going to do your calculations. This thing is 2.5 times better than most of the stuff you're going to calibrate. Why are you in the world are you going to go spend close to 20,000 on this indicator over here to get you a 14 or 15-to-1 when you can buy this $6,000 indicator? Well, what happens even at 2.5-to-1? If I'm running a lot, this is batch quantity, right? Over here, let's just compare these two. Over here, huge differences, right? Falsely accepted. I accepted 1,000 items that I said were good that were actually bad. Over here, 639. Falsely rejected, 9,611 and 28. So production costs, depending on what we're running. I hate this thing when it does different stuff, but depending on what we're running over here, this is where all this heart of this discussion comes in. Production cost stays the same, right? I'm going to make X number of widgets, right? 1.35. Cost due to false rejection, where that person tried to sell us that $6,000 indicator. If this was monthly, it's $129,000 going out the door compared to, I think it was over here, um, compared to $373. How long does it take for that extra money to pay for the extra cost to pay for itself if this is monthly?
Probably within the first month, if we're talking about between the Acme Standard and the Acme Gold.
First couple of days.
Yeah.
Look, 120, this is what I'm rejecting a month.
Well, you said with
129,000.
how many months, so I wasn't gonna get
Yeah.
into what
So if this
percentage
is
of
a
it.
month, 129,000 is going out the door per month in this scenario, and 373.69 is going out. The difference in price of these two is $13,492. So, yeah, depending on working day, if I had 20 working days, divide 20 by 129, um, yeah, it doesn't take long to make up that additional 13,000. And if we look at that from false, I mean, the difference in equipment cost and the difference in saving from the very the lowest buck to the best was like 464,000 a month. Um, Pretty significant when you look at it. And people do it all the time. They buy the wrong equipment. They have these high ratios, and then they throw out good product. And this is just a slide that says, hey, if I use method six versus method five. Method five is more aggressive. You have a higher PFR. You really need to break down into decision rules using this. Or method six is this global risk model that Michael Dobert came up with. It's really an ingenious model that is you can control your risk, your PFA and PFR to as long as your TUR is over 4.6 to 1, it can hold it. But method six holds it to 2% no matter what. But you still have a lot going on here in this curve. And what Greg's showing is, yeah, as your TUR is hot, look at this, like TUR at 1.5 to 1 in this calculation, 52% failure rate. And this is very strict method, and 15.82 at 3.5 to 1. But you use a different method, the TURs change. But for what we're looking at, overall, you start looking at the total project and look at how much does it cost when you reject a product as a percentage. And if I'm buying this cheapo DMM indicator, I'm rejecting 24,970 and I'm falsely rejecting 250. And then down here, if I buy the absolute best indicator, now my number falls pretty drastically to 40 parts per million. 40 out of every million is being rejected um, versus 0.25%. So pretty drastic numbers overall when you look at this. And what does this do? You could start looking at costs. This is just a model about upfront price tag. If we had a BCM, here's a UCM. This could be an automated UCM that reduces more error with force measurements. And when you look at it, you could say, hey, the BCM cost me X amount of money, and the automated UCM cost me 10 times that amount. And then you start looking at, well, what's my rework cost? If I'm rejecting 30%, saying 30% I'm going to, of my, everything that I say that is bad, 30% of that is actually good. So my retest and rework cost is going to be a lot higher there than if I have a 4 to 1. So if I buy the better equipment over here, this chart's pretty cheap. Extra cost per year basically uh, comes out to be $3,000 difference versus $500 difference. So maybe you don't spend 10 times as much uh, depending on what you're testing. Of course, this all relies on different ratios. So if you want to test equipment that's like 0.1% of full scale, this might be a lot different scenario than if you're doing something that's 0.5% of full scale. And running the different numbers just shows you that, hey, the higher that TUR or measurement, the capability index goes, the more cost I'm going to have and the more rework I'm going to do, or the more calibrations I'm actually going to make the determination that it's bad when it was actually good happens. So
Right.
Every wrong decision results in unnecessary cost, extra analysis, and even potential recalls, all due to bad decisions from using equipment with high measurement uncertainty. So,
Also, can you go
takeaway.
back real quick?
Yep.
Um, not related to necessarily false rejection and cost, but that's not the only thing to look at when making an investment for one of these machines. Like you were
No.
mentioning the automation too. I
Yep.
mean, that can cut your time down, that can
Yep.
free up technician time too.
Nope.
There's a lot of other value too. So this $2,500 difference per year is really actually higher when you look into other factors.
Yeah,
So,
if you read the paper, it was based on like it's costing you $50 per hour. Most people, it's costing a lot more than that. So these numbers are relatively low. I
mhm,
wanted to just keep the graph here and say so someone didn't say I'm overinflating or underinflating them, but this is just based on rework alone. It's not based on throughput. Yeah, your point is not based on anything else.
right,
I mean, if you have three technicians that are all making mechanical measurements, as long as they can align the load cell and wire it up correctly, the automation is going to make the repeatability between those technicians next to nothing, right? But if it's a manual process where they have to actually have to hold and control the force with some kind of pressure pump or valve or
right.
jack or something else, there's going to be more variation in that process, which is going to kick up the overall measurement uncertainty, which is actually going to lower things, and more of this is going to happen. So
Yep.
takeaway is higher TR dramatically reduces false rejections, which is the main benefit of moving from like say 2 to 1, 3 to 1 to 4 to 1. 4 to 1 seems to be the magic number. It started in the 1950s. Jerry Hayes, 3 to 1 was the number that they thought, and then they buffed it to 4 to 1, and it just basically maintained 4 to 1 TER for ages. But then Paul Reese and John Harbin did this awesome paper that they ran all these samples and calculations using method 6, and at really at this 4.6 to 1 or higher in method 6 context, measurement uncertainty is small enough relative tolerance that the PFA, that probability of false accept, is held to less than 2%, assuming the method's conditions. So if we look at this, these are all risk curves with different TURs. PFA percentage with a 1.2, at 6% intolerance probability down here, or end of period reliability. And then you look at the PFR percentage, 10 is higher on that one than it is there. So you're going to, again, and you're just going to do more rework the higher the uncertainty. And once you get down to these 4.6 numbers, this low number, your PFA in all of these and your PFR, uh, if I can highlight it right there, Brett,
Hmm.
is well under 2%, right, for both of these curves. In fact, at 4 to 1, it just nips over. If you look at it, that's this blue curve here. Over the 2%. It does go over 2% for PFR, but you can see lower TUR, the less work. Yeah, at 2.0 PFR, it's still significant. So you have lots. Another question: what if the tolerance were plus or minus 5 in the CMUM clay? So what do you think happens here? This is the TUR of 1 to 1. What did we learn?
We learned that for the 1-to-1 that's going to be a higher probability of false accept.
Yeah. So there's a good chance the calibration provider adjusted something that may have actually been good. And if we assume they had a 10 to 1, basically chances of anything happening is very low, and they can say the device is still in tolerance. So you calibrate lab 1. You use this to calibrate other instruments. Reference standard loaded to 10,000 when it's actually 9991. Total risk. Remember, they're telling you something's good when it's actually bad and they have high measurement uncertainty. So they use that measurement, make another measurement, and the risk just balloons. Where what happens if they send it to us with 10 to 1, 20 to 1 TUR or measurement capability index? That risk, same scenario, risk drops to next to nothing. So the lab, in one scenario, if we go back, that lab that has the high uncertainty gives you a device and you go and start using it, and now you start putting the risk onto all of your customers and all their devices, where you use the lab with the low uncertainty and you start using that device, and now everything starts passing calibrations. So ultimately rejecting them so that is actually good is going to lead to more rejections and has the potential to call instruments good that are actually bad. If the system and measurement chain work correctly, the lab where the instrument was adjusted when it should not have been should eventually notice failing more instruments than it used to. Basically, you switch calibration providers for price difference, meaning you were going with a good calibration provider and went to Calibrations R Us, a cheap calibration provider, because they quoted you a third of the cost or whatever. Now they're saying they adjusted your instruments that had a 10-year history that were never adjusted. No one picks up on it because you hired your quality person right out of school that doesn't look at anything and know any better. And they keep using it to make more and more measurements. You start correcting things, and someday a technician says, "Hey, I'm rejecting." Um, Maybe they care. Maybe they come and say, "Hey, someone eventually looks at it and say, out of the last 5,000 calibrations, how come we rejected 1,500 where we used to reject 50?" Uh, if they even see it. And this assumes people are paying attention to all of, and they can, like I said, they can go unnoticed. Also, the risk of lower cost providers and everything else. So once you get through it, the cost ladder of PFR retest, that's internal. That's really cheap. We do that. We retest a lot if we think we made a mistake or do something. You're back in the lab, right? You know that this, if you get it before it goes out the door, it's a lot less expensive than when the
Yeah.
customer gets it and they say, "Hey, I don't think it's right." And then you say, "All right, let's issue an RMA, let's return it." Sometimes right, sometimes wrong. If you have high uncertainties, the chances of retesting it and finding a different result can be high. And then it could lead to an unnecessary recall. So you have retest minutes, RMA, which is days lost, and then unnecessary recall can be weeks, can be months, and that cost can just escalate exponentially. So if we wanted to mitigate everything, we can raise our tolerance. We don't have to say what the manufacturer states. I mean, give you an example where where the person actually cared about a 5% measurement with a 0.7% device, and probably very low risk there. We can decrease our time between calibrations. Maybe it's a matter of a two-course resolution where a different indicator would help. We didn't talk about that too much, but that's part of the denominator in TUR. And we can use calibration providers with low uncertainties. We can buy better equipment. So what I really want people to take out of this is evaluating that likelihood and consequence, right? And what is the risk to your business if the accounting department, picking on accounting, they're not all bad, but if the accounting department says, "Hey, if we have a choice between a $6,000 piece of equipment and a $20,000 equipment, the $6,000 two and a half to is good enough." Is it good enough? And that's where you really need to go at, like, how many devices am I going to reject? How much? What is the likelihood and consequence of all those of all of that? My production cost, and if I let something out that's bad when I say it's good. So how am I going to control that? There's so many different ways and methods to do this. The standard doesn't say you have to do all this stuff. All it says is, like, when we start agreeing on that conformity decision on pass and fail, that measurement of certainty must be taken into account. Doesn't say a lot of other things. These are all things, decision rules and everything are things that you make the call on what you want. You control your uncertainty, you control your process, you control the measurements you make for other people. They control if they send it to you. If they are educated and know the repercussions, uh, maybe it's time that you made some effort to lower your uncertainty. I don't know. You want to add anything?
Uh, I don't really have much to add. I think you've covered it pretty well.
Yeah, we can use combination of these control charts, just things you can do. You can run the so talked a lot about that, but yeah, if you are monitoring your process well, you might have the ability to switch cal providers and see what happens. But hey, maybe this is a month, this is IMR chart, but maybe this is where I switched cal providers up here, and then I went back to my normal cal provider down here. If you have methods in place, always good to monitor your false reject rate. This is a P chart, which is the tracking the false reject rate over time. But yeah, if it bumps up, what do I correlate it with? Is this training a new tech? Is this I went to a different provider? Is this my current provider was backlogged, so I did this or so many different things can happen. I don't know that many people that are doing this, so your best step is probably just to use your calibration provider with the lowest uncertainties. But if you do this, it can show a lot of trend analysis and detection is always a good thing. So, but monitor how often the lab false or rejects intolerance items. I just had this, Brett, and Brett edited a high-low when people send a load sewing that's 10,000 pounds and they say it's 10,000 pounds high range and they get a low range calibrated. Did that full analysis and determined that the low range percentage-wise is always going to be higher overall percent of full scale than
Right.
the lower range. But the reason that happened was a customer was questioning their data. And I went back and said, "Hey, our lab," I said, "Hey, like this is the high range is the lowest it's ever been over the last 10 years. And the low range is the worst it's been by like two or three standard deviations more. Can you recheck it?" The tech rechecked it, and he said he thinks he had an alignment issue at the time of calibration, and then everything came in. But if you're not monitoring and looking at this was before the instrument went out, so we're on that rework phase while it's still cheap and not costly for the customer. But yeah, the point is like we are not infallible. Everybody makes mistakes. We have really low uncertainty, but paying all this attention to the charts and the historical data allow you to find this stuff really quick. And that's a situation where we had all that cal data that we go back and say, hey, yeah, something's wrong here and find it. And that's with low uncertainties. So high uncertainties, sometimes you can't see anything. You're just like, yeah, that's how it is, and then somebody has to live with it and here, take it. But yeah, consumer risk, depending on the criticality, you have loss of life, remission, reduced end item functionality. The Hubble telescope's a great example of what happens in all this risk stuff where it was $1 million calibration, but the lesser calibrations actually told them they had a problem and they didn't want to redo the $1 million calibration, so they sent it up, and it was only like $2 billion to fix it. But
Hmm.
warranty expenses, damage to corporate reputation, loss of future sales, punitive damage, legal fees, and everything else. But you know what the silver lining is, Brett, on all of that? Is we got an IMAX documentary that Leonardo DiCaprio narrated, and I know you've probably watched that
Yeah.
5,000 times because you're his biggest fan.
We
Okay,
watched it
so
in 3D back in the day. I think it was like
yeah,
back
we
in like
did.
2013. Yeah.
We did watch it, and that documentary is really cool. We got that out of it. Brett and I got to spend father-son time watching Leonardo DiCaprio narrate a 3D IMAX movie because of that billion-dollar plus mistake. So, yeah. Other things can result in additional costs, unnecessary rework, adjustments, increased scrap of good product, frequency of inspections, all this stuff. People do stupid stuff all the time. Let's. We had one failure let's put in a practice in place, a non-value add that we test absolutely everything when we had one failure out of, 10,000. Overreact that way too. So no one's immune to all of this, but uh, it's worth looking into. Like when we have that failure, like, yeah, what did I do? Did I switch providers? Did I switch adapters? Did I do something else that I normally didn't do? If it's out of the ordinary, and monitoring it is always a good thing. So, three practical approaches. You have shared risk. That's basically say, hey, I can use up to the tolerance. Um, spec limits. If I'm just using specific risk or bench level, this is where I could have a 50% PFA PFR. Once I go to a more global risk scale, like when I'm looking at the population and I have the tolerance limit, even if I'm at 50-50 and I like am using this high TUR on the global scale, my risk is going to be super low. So you really need to decide, am I going to use it based on like, is this really a critical application where I need that bench level risk, or can I use this more of a population? And I'm really simplifying this. So if anybody's on here and like a read all the documents, just know that yes, it's a little harder to get into than that. But you can make shared risk with TURs, and it like when you're on the global scale, and that's can control your risk perfectly fine. um, if you have, the constant PFA guard band that's applying, you're going to have the penalty of probably the higher PFR. So the having that ratio be higher is good. But yeah, you moderate 2 to 4 customer risk focus. Chances are you're going to maintain your PFA targets. So you're not going to say anything's uh, good that is actually bad on the PFA side, but you're going to say more things are bad and do adjustments. So you're going to pay the penalty of penalty of PFR over here. And then you have conditional accept reject result plus the measurement uncertainty plus rule, low TUR complex specs. So just when you could use it, you don't have to. I'm not one like, it all depends on your likelihood and consequences. So um, they don't guard bands do not reduce your measurement uncertainty. They define how we use uncertainty in measurements to make conformity decisions and allocate that decision risk, producer versus consumer. Better measurement process is the most direct way to reduce both risk, but a documented decision rule is still required whenever a statement of conformity is made. If uncertainty isn't accounted for, the risk is undefined, undefiable, and the decision can become technically worthless or misleading. And this is my joke. But Brett would hate me because he'd have to write all this out and say it's too long for social media. Know your measurement uncertainty and choose an appropriate decision rule. Then reduce the uncertainty where it matters most to minimize decision risk and avoid unnecessary false rejects. That's way too long. So expanded uncertainty should include all significant contributors. We put that slide in. Guard band choice, tighter guard bands narrow the acceptance interval. So they lower the PFA, but typically raise the PFR. So you have that trade-off. More good items fall outside acceptance. Higher TUR measurement capability index generally reduces both false accept and false reject probabilities for fixed decision rule. Lower MU effectively makes decisions more reliable, less overlap near limits. And then choosing better equipment plus better calibration reduces decision risk and avoids unnecessary guard band fallout. And just know that, yes, if you do this and go with that better provider or go with the better equipment, you still have risk. But if you're doing the right things from those sheets, there's a lot less of it, and you should make a lot more money from making more of the right decision or passing more product. So, that being said, I could talk forever on these topics. Want more? There you go, Brett. 6K metrology professionals on LinkedIn. Take us home. Uh,
Yeah.
what
Now,
else?
now you'll see, I believe, for the number that you guys will see on it will be about 7,000. But we're still a little bit under that, so still growing. And then yeah, we have YouTube videos that we put out. We have our Insider, which we advertise through social media. We have it on our website. A lot of blog posts too. There's plenty of free educational content that you can access on our website, and like Henry highlights here, a lot of free downloads too.
So, all right. Well, thank you, everyone.
Yeah, thank you
Anything.
guys.